Okay, so I'm gonna kind of recap where we were, because I'm kind of confused about where we actually were. So we were in chapter 6, and I think in a video I had gotten to, we discussed all the orbitals, right? And so all the orbitals were these probability distributions of where the electron was likely to be in the atom. So we looked at all the various orbitals. We had um, the s orbital, we had the p orbitals, the d orbitals, and the f orbitals, and we looked at the various shapes of all of those orbitals. And this is particularly for hydrogen. We had talked about all of the quantum numbers. So all of these orbitals are specified by sets of quantum numbers, right? So we had 3 different quantum numbers, n, l, and m sub l. And then we had introduced you to a 4th quantum number right at the end, right? And so the orbital is actually going to be specified by the first 3 quantum numbers, but then the 4th quantum number doesn't really have to do with the orbital. It instead has to do with the electron, and we call that 4th quantum number the spin quantum number, and we give it this little letter m sub s, or this designation m sub s. And so m sub s only had 2 possible values, right? It had a plus 1/2 value or a minus 1/2 value. And we also called these spin up and spin down, and we would denote that via this little half arrow pointing up and this half arrow pointing down. Okay. All right. So then we talked about hydrogen, right, and how the hydrogen atom only has 1 electron, right? It has 1 proton in the nucleus, and we know that that 1 electron wants to go into the lowest energy orbital, right? So the lowest energy orbital is going to have the lowest principal quantum number, right? And so the principal quantum number is n. So the lowest value for n is n equal to 1. And then if n is equal to 1, L is equal to 0, and m sub L has to also be equal to 0. So remember, there are all those little rules with respect to our principal quantum numbers. So this guy, this orbital with principal quantum numbers, or quantum numbers of 1, 0, 0, this specifies the 1s orbital, right? Because the value of 0 for L, we gave it a letter designation, we called it s so that it wouldn't get confusing, okay? So this is the 1s orbital. This is the lowest energy orbital, again, because it has n equal to 1, which is the lowest principal quantum number. There's only 1 electron, right? And so we just said, okay, well, that electron is going to go into this 1s orbital. And so we denote that via electron configuration by putting a 1s1, okay? Okay, so, and we usually, if we were going to write this, so this is what we call electron configuration. We can also denote this via what's called an orbital diagram. So in an orbital diagram, we represent our orbitals as boxes, and then we'll label which orbital we're dealing with on the bottom. And so for the first electron, for hydrogen, we would just put this in here as spin up, right? So plus 1/2. And so this would be the orbital diagram for hydrogen, okay? All right, so that was hydrogen. And that was great because with hydrogen, we could actually solve the Schrodinger equation, right? All these orbitals essentially came from the hydrogen atom, right? As we moved up, though, to multi-electron atoms, so if we move up in the periodic table to helium, helium has 2 electrons. It has 2 protons in the nucleus, so neutral helium has 2 electrons. We can't actually solve the Schrodinger equation exactly for anything that has multiple electrons. Okay, so this was kind of like, well, we built all this up, but then we can't actually solve it when we move on to more difficult systems. So we can, instead of solving it, we can determine approximations, okay? And in those approximations, we were able to show, or we weren't, but scientists were, that anything with multi-electrons does have orbitals, and these orbitals are hydrogen-like. Okay, so we're going to use these same s, p, d, and f orbitals to figure out where these other electrons are going as we start to add more and more electrons as we build across the periodic table. Okay, so we got to helium, right? And so now we have 2 electrons. We need to figure out, comparatively to hydrogen, where does that second electron go? Okay, and so that's when we had introduced the Pauli exclusion principle. So in the Pauli exclusion principle, so Pauli exclusion principle, Pauli exclusion principle had stated that no two electrons in an atom could have the same set of 4 quantum numbers, right? And so remember that the orbital was designated by N, L, and M sub L, right? So there was 3 quantum numbers that specify the orbital. And again, if we're talking about the 1s orbital, if I wrote the N, the L, and the M sub L values up top, the first electron for helium in the 1s orbital would go in 1, 0, 0. The second electron would also have 1, 0, 0. And the only way these guys would differ would be in M sub s. Right? So M sub s is spin quantum number. It can have values of +1/2 and -1/2. And so those 2 electrons in helium, they were both going to go into the 1s orbital, and they're all going to have a different set of 4 quantum numbers, right? They have the same exact orbital quantum numbers, but then they differ with respect to M sub s. So we can know that for helium, 2 electrons, both of those electrons are in are in the 1s orbital. Okay, and when I'm writing this and I'm denoting this, I'm noting that this is the orbital that they're going in, and this is the number of electrons. Okay, so hydrogen, helium. This again is the electron configuration. So this is the E configuration. I could also write the orbital diagram here. And so again, this is the 1s orbital. Now my first electron goes in, spin up, and then that second electron for helium goes in and spin down. So now they are spin paired. Okay? All right. So kind of keep building, right? So then we had gotten to the point where we're like, hey, what about lithium? Right? So lithium has 3 electrons, right? So we move across the periodic table. Lithium has 3 protons. It also has 3 electrons in the neutral atom. So we know that the first 2 of those are going to go into the 1s orbital, right? Just the exact same ideas that we utilized for helium. Now the question is, where does this third electron go? All right, where is it going to go? If we try to put it in 1s, then we would have to repeat our M sub s, and there's only 2 values, right? The big implication behind Pauli exclusion is that there can be no more than 2 electrons in an orbital because there are only 2 values of M sub s. So it can't go in the 1s orbital. So now the big question is, okay, we're going to move on, right? We're going to increase the quantum number, right? So this was the orbital for n equal to 1. What are our possible orbitals if n is equal to 2? The next little principal quantum number up. So if n is equal to 2, if we remember, L can have values of 0 and 1. Because remember, L goes from 0 all the way to n minus 1. N minus 1 here is 1. Okay, so we have 2 possible values of L. So L0 is the s orbital. So this would be the 2s orbital. And then L equal to 1, we represent it as the p orbital. So this would be the 2p orbitals. Okay. Also remember that for s orbitals, values of 0 for L, there is only one possible value of M sub L, and that was 0. So that tells us there's only one s orbital. Okay. On the other hand, for p, our M sub L values, which tell us our orientation in space, can be -1, 0, and +1. So that tells us that there are 3 p orbitals, right? Or not, I shouldn't put 3p because you make it seem like 3p, but there are 3 p orbitals. Okay? Orbitals. Okay? And they all differ in their orientation in space. So we can say there's a px, a py, and a pz. Okay? So now, if we go back to hydrogen, I know this is like, where are we getting at with this? Who knows? I just need to remind myself where we are. If we go back to hydrogen, and we had looked at the energy of these various orbitals, we went back to the hydrogen atom, we found that lowest energy state was n equal to 1, right? And so this was the 1s orbital. But then for hydrogen, as we move to n equal to 2, where we have our 2s and then our 3 2p orbitals, these guys were all equal in energy. So everything for hydrogen that had a 2 were all equal in energy orbitals, and we called that degenerate. right? So the next big question as we move through this is like, okay, so we put 2 electrons in. Where does this third electron go between the 2s and the 2p, right? Do I put it in the 2p? Do I put it in the 2s? And again, we're questioning this for lithium overall, okay? Now, these guys, 2s and 2p, these were degenerate for hydrogen, right? For hydrogen atoms, there is no energy difference between s and p, so it wouldn't necessarily matter where it went. As we move into multi-electron atoms, though, which is what we're dealing with for lithium, there is going to be a difference in energy between these two. And that's what we're going to develop now, right? Who's lower in energy? Where's the electron going to go now? Who's higher in energy? Who's going to get filled later, okay? I'm going to go ahead and cut to the point on this one. And I'm going to tell you, like, the moral of the story before I actually even get to explaining the moral of the story. But overall, what we're going to find as we move up into these higher principal quantum numbers is that the s orbitals are going to be lower in energy than the p orbitals, lower in energy than the d, lower in energy than the f, okay? Now, that's what's going to happen. If you're happy with that and you don't want to be explained why that is, please skip to kind of like the end slide of this and you will be happy and satisfied. But if you're not happy with that and you want me to explain why exactly this is, then you should continue on with me on this journey through quantum mechanics. To the next slide. Okay, so I'll try to quit being so verbose in my explanations. But as we develop this question about where does the next electron go for lithium, right? So lithium with its nice little third electron, where does it go? Is it going to be in the 2s versus the 2p? That's kind of the question that we're asking. We're going to bring into play a couple of other concepts, right? And these other concepts are going to be important. We're going to kind of come back to them. So it's important that we kind of introduce them now. The first one is Coulomb's law. Okay, so Coulomb's law deals with interactions between charged particles, right? And what it deals with is potential energy interactions between charged particles. So overall, we're going to call this guy, this E, we're going to call it potential energy. And this is electrostatic potential energy. My iPad has not been happy with me today. Okay, so potential energy, electrostatic potential energy, right? Coulomb's law is kind of, I guess, big, right? There's a bunch of stuff that we don't really care about, right? So this stuff right here, all of this is just a constant, and it doesn't play any role in how we can understand Coulomb's law and this electrostatic potential energy that occurs between charged particles. The big meat and potatoes of Coulomb's law comes in here, okay? So most of you probably are familiar with Coulomb's law. The Q part here is dealing with our charged particles. So Q1 would be, let's say, charged particle number 1. And then Q2 would be charged particle number 2, okay? And then the R here is the distance between them. So R is distance between them. Okay, so overall, with respect to between them, I can't do multiple things at once. Okay, so overall, with respect to interactions between charged particles, lower potential energy is going to be good, right? So the bigger and more negative this E, this potential energy is, the more attraction there's going to be between our particles, right? So how are we going to get this big and negative? So if we consider, let's say, a proton, which has a positive 1 charge, okay, and an electron, which has a -1 charge, and we consider this distance between them being this R, if we plug this into our little Coulomb's law here, we have E is equal to, I'm going to ignore the constant part because that always is there, it doesn't go away. So we have a +1, a -1 over R. So overall, this is a -1 over R, right? So this is going to be a negative number, which is good. It's a lower potential energy, okay? And as we bring these two things closer together, as we make R smaller, this negative energy, or this potential energy, is going to get negative and larger, right? So we're going to be lowering potential energy as we bring these two guys closer together, right? So that's going to overall lead to this very attractive force, okay? On the other hand, if we had two charged particles like a proton and another proton, right? And again, they're separated by this distance r. Then if we wrote this for Coulomb's law, again, ignoring the constant, we have a plus 1 over r. So overall, this would be a plus 1 over r. This would get positive and larger the closer we brought these two things together. So as r decreases, this potential energy is going to get positive and larger, which is bad, right? This is what accounts essentially for the repulsive effect between light charges. Okay, so we always want to lower potential energy. Also note that magnitude is important here. Okay, so for example, up here I had used a plus 1 and a minus 1, but let's say I had a nucleus that had 3 protons in it, right? So 3 protons in the nucleus would give me a positive 3 overall charge, right? If I'm looking at the interaction between positive 3 nucleus and a minus 1 electron, and again, this is going to be larger, right? Comparatively to a plus 1 and a minus 1 up top, our potential energy is going to take into account the magnitude of this, right? So this would be a plus 3 and a minus 1 over r. And so overall, this would be a minus 3 overall. Minus 3 over r. So comparatively, this is a much stronger attractive force than this guy because, again, the magnitude of the charges come into account here, right? So as we decrease r, this is going to get big, and it's going to get big and negative, and it's going to be much bigger negative than this guy up here because, again, that positive 3 has a much stronger attractive force, or much stronger attractive pull towards the nucleus. Okay, so Coulomb's law is number 1. And again, it's going to help us understand all of these various interactions and how they are going to lower potential energy, which is what we want to do. Okay, so just to kind of reiterate that, here's a nice little question that utilizes what we just learned. All right, so according to Coulomb's law, what happens to potential energy of two oppositely charged particles? These are oppositely charged particles as they get closer together. Another way to look at that is as r decreases. So you have 3 choices, A, B, C. I would think about it, push pause, and then find out the answer after the break. Okay, so potential energy, Coulomb's law, right? So potential energy with respect to electrostatic potential energy is proportional to the charges and inversely proportional to the distance, right? If we have 2 oppositely charged particles, and let's say we have a plus and a minus, and we brought those 2 guys closer together, then when we plug that into Coulomb's law, we have a plus and we have a minus over r. This would be a negative over r. So as we brought these 2 guys closer together, as r decreases, then what we're going to see is a larger and more negative potential energy. So overall, more negative. Man, see, I can't write and talk at the same. More negative. So I should just stop talking. Potential energy. Okay, so what does that mean? Larger, more negative? That means the potential energy decreases. It gets bigger, but it gets more negative. So that is a decrease overall in potential energy. The correct answer is A. Okay, so let's look at a couple other things that are going to affect this little electrostatic potential energy so that we are capable of figuring out who's lower in energy, the 2s or the 2p, okay? So another little thing that we're going to think about is something called shielding, all right? So we're going to go back to lithium. Lithium, again, is kind of where we've been stuck at. So lithium has 3 protons in the nucleus. It also has 3 electrons, right? And we know where the first 2 electrons are. They're going to be in the 1s orbital, okay? All right, so that 3 proton in the nucleus means that there are essentially plus 3 positive charge from the nucleus, right? So when we think about Coulomb's law, that plus 3 is going to manifest itself, right? So that plus 3, when it's interacting with our little third lone electron out here, is essentially going to be pulling it with a magnitude of a plus 3, right? Now, that would be the case if this lone third electron wasn't in the presence of the other two, right? So if we have a +3 pulled towards the nucleus right now, these two also play a role here, right? And so since this is an electron, and this is an electron-electron interaction, the presence of these first two electrons that are in the 1s orbital is going to have a repulsive effect, right? Because this would be E equal to -1 times -1. So these are similarly charged particles, right? Divided by R. So this is overall is going to have a +1 over R. So this is going to have a repulsive effect, and it's going to be in the magnitude of a -1. Okay, I know the signs are kind of confusing, but just stick with me here. Okay, so the same thing's going to happen here. We have a -1, a -1, so this is also going to have a -1, right? So this electron feels a pull towards the nucleus, right? But it also feels simultaneously a repulsive effect from these two electrons that are in what we call a filled shell, a lower energy shell. Okay, so overall, because of that, this third electron does not feel the full pull of the nucleus. It only feels a +1 magnitude overall towards the nucleus because, again, of the repulsive effects between these two electrons in the filled 1s orbital. Okay, this is what we call shielding, right? What these electrons are doing to this electron out here is shielding that third electron from feeling the full pull of the nucleus, right? And so because of that, this electron only feels this +1 pull, right, because of the counteractive forces of these two electrons. We call this +1 something called the effective nuclear charge, right? So this electron effectively only feels a +1 pull from the nucleus, even though the nucleus has a full nuclear charge of a +3, okay? So effective nuclear charge, that's the attractive force that this third electron feels because, again, of the presence of these two repulsive electrons here. Okay, so, that's not great. If this electron could somehow get really close to the nucleus, then it would be able to feel the full pull of the nucleus, which would be nice and stabilizing with respect to electrostatic potential energy. So there's one other little concept that we have to consider, and that is something called penetration, okay? So, again, that third electron that was hanging out here only felt an effective nuclear charge of a +1 towards the nucleus because of these guys, the presence of these guys, okay? Now, if somehow, every once in a while, that third electron got to penetrate into this 1s orbital and get really, really, really close to the nucleus, then this would be nice and energetically stabilizing, or this would help lower the potential energy because, again, now it wouldn't be shielded from these guys, and it would get to feel the full attractive force of the nucleus, the full +3 draw towards the nucleus, which again would lower its potential energy, going back to Coulomb's law. Okay, so a couple things to consider. Shielding, bad, kind of destabilizing a little bit because it doesn't get to lower the potential energy of that third electron. But if you do get to penetrate into this filled inner shell, then you will get to feel the full effect of the electron, and again, that will lower your potential energy. Okay, so again, this whole entire purpose was to say who is going to get the next electron, who is lower in energy, the 2s orbitals or the 3 2p orbitals, okay? And so now we have this idea of shielding as well as penetration, and we also understand how these various electrostatic interactions are lowering potential energy, okay? So now we're going to move on to what is called the radial distribution functions, right? We had talked about this with respect to our quantum mechanics. So radial distribution functions plot the probability of finding the electron a given distance r from the radius, right? So it's this nice little spherical shell r from the radius, right? We have plotted right here the 1s probability distribution, and so 1s is really close to the nucleus, and it's probably going to have a maximum somewhere out here off the chart, okay? We've also plotted the 2p and the 2s, okay? And so if we look at this, we'll find that the 2p orbital is actually closer to the nucleus, right? Its maximum probability, which is kind of like the peak in this plot, is closer to the nucleus than the maximum probability of the 2s, right? So if it's closer to the nucleus, then you would think that 2p, since r is smaller would have a lower potential energy, right? So it would be lower in energy because, again, 2s has a maximum probability farther away from the nucleus. The nucleus, again, being right here. And that would be correct if it wasn't for a little bit down here, right? So 2s is this red thing, right? And notice that for 2s is spherically symmetric, but we also have a node right here, right? And we also have a region right here of probability that gets really, really, really close to the nucleus, right? This little bit of probability in the 2s orbital penetrates into the 1s orbital. And so for a small fraction of our electrons in our 2s orbitals, small probability of them actually get really close to the nucleus and penetrate and essentially aren't shielded by the 1s electrons because of that, okay? So big long-term ramification of this is that because 2s penetrates into 1s and gets its electrons really close to the nucleus, the 2s orbital ends up being at a lower energy state than the 2p, even though the 2p has a probability of being closer to the nucleus, okay? Okay, so when we're asking this question of where does the third electron for lithium go, it's going to go into the 2s, right? And the fourth electron is also going to go into the 2s because, again, we are going to fill our orbitals, and each orbital can take on 2 electrons. So that is the 2. So n equal to 2 gave us this L equal to 0 and 1. So that's what we've dealt with here. We move on to n equal to 3. So if n is equal to 3, our possible values of L are 0, 1, and 2. This is the s orbitals. L equal to 1 is the p orbitals. And L equal to 2 is the d orbitals, right? So what's going to happen with these guys? How are they going to be spaced with respect to energy? So if we look again, notice that the 3s orbital is actually maximum probability farther from the nucleus than the 3p, than the 3d. But again, with 3s, we get this nice little penetration really close to the nucleus. We get 2 little bits of that really close to the nucleus. 2p also has a little bit of penetration here. So it has this green bit of penetration. And then the 3d doesn't have any type of penetration. So with respect to energies for these orbitals, we're going to have the 3s orbital at a lower energy state than the 3p at a lower energy state than the 3d. Okay, and we can even move that on when we move to 4. 4s would have a lower energy than 4p, would have a lower energy than 4d. And then with n equal to 4, we also bring in the f orbitals. It'll have a lower energy than the 4f. Okay, so that's great. Now we can kind of start understanding where these electrons are going to go with respect to these orbitals and with respect to the lowest energy state. One other thing I want to note is that if we go back to hydrogen and these energy spacings of these principal quantum numbers, so remember our first principal quantum number was n equal to 1, and then we had our second, n equal to 2, and then we had our third, n equal to 3. As we increased the principal quantum number, the distance between these levels got smaller and smaller, right? The energy difference between these levels got smaller and smaller. That's going to manifest itself when we actually start putting our electrons into orbitals, okay? So what happens as we get up to n equal to 4 and n equal to 5, which would be something like here, is that we're actually going to start to see mixing between these orbitals with respect to who comes next in line, okay? So overall, what we're going to look at is this following diagram, right? So electrons are going to always go into the lowest energy orbital that they possibly can, right? We know from Pauli exclusion that only 2 electrons are allowed into an orbital, okay? So what's going to happen is we're going to fill the 1s first, then we're going to fill the 2s, then we're going to fill the 3 2p's, the 3s, the 3p's, then it's going to come the 4s. You would think it would be the 3d's, but again, as we increase the principal quantum number, this distance between these levels gets smaller. So actually, energetically, the 4s is at a lower energy state than the 3d, then the 4p, and then 5s and 4d. Okay, and again, we're going to start to fill or write these electron configurations here in a second. Hopefully that'll make more sense. one nice little way to kind of remind yourself of this, and this, I guess, order of ordering, or how you're actually going to start putting electrons in, is if you write out the orbitals. So 1s, 2s, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and then there's a g. Right, so if we just write out first principal quantum, second principal quantum, all the orbitals involved, third, etc. And then if you use just an arrow, so electrons are going to go into the 1s orbital first, then into the 2s, then they're going to go into the 2p, and then the 3s, 4p or 3p, and then the 4s, and then 3d, 4p, 5s, and so on and so forth. Okay? So this is like a nice little thing to help you memorize how you're actually going to order the electrons in these orbitals. Okay, so why don't you guys go ahead and try this little question. I'm not going to read it because it's too much. I want to know which of these 4 statements is true. So go ahead and pause this and then come back for the correct answer. Okay, so what we're looking at here is these various ideas behind shielding, like shielding of outer electrons, as well as how orbitals that penetrate into areas that are very close to the nucleus, how that can help stabilize our various orbitals and then lower the energy, or stabilize our electrons and lower their energy. Okay, so for A, we're talking about an orbital that penetrates into a region occupied by core electrons, is more shielded from nuclear charge, and will therefore have a higher energy. So an orbital that penetrates into a region occupied by core electrons is less shielded, right? So the best, or this should, if it was true, this should say less shielded. And therefore will have a lower energy. So then in B we have an orbital that penetrates into a region occupied by core electrons is less shielded, so that's great. Then an orbital that does not, and will therefore have a higher energy. So no, it will have a lower energy. That's the whole purpose of all of this with respect to Coulomb's law. So not A, not B. An orbital that penetrates in a region occupied by core electrons is less shielded. That's good from nuclear charge. Than an orbital that does not, and therefore have a lower energy. So that sounds about right to me. On this last one, an orbital that penetrates into a region occupied by core electrons is more shielded. No, and it will have lower energy, but it's not because it's more shielded. So the correct answer here is C. Okay, so we're going to start to put these electrons, now that we know the order with which they will go to obtain their lowest energy state. Now we're going to start to put these electrons into our orbitals, okay? So we're going to be building from the lowest energy state to the highest energy state, or the lowest energy orbitals to the highest energy orbitals. So we just went through the various energies of the S, P, D, and F, given their principal quantum number. This idea of building up from the lowest to the highest is what is called the Aufbau principle. And Aufbau is German for build up. So we'll get into this. So if we have orbitals that are at the same sublevel, they're going to be degenerate. They will have the same energy. What this means is, for example, we have 3 2p orbitals, right? So we had 1, 2, 3. These are our 2p's. This is what we mean by the same sub-level, right? They're in the same sub-level, so all of these 2p orbitals have the same energy. So there isn't going to be necessarily a preference on which one we put them in first. And then again, no more than 2 electrons in an orbital. That's given to us by the Pauli exclusion principle. And then there's one last little rule, and that's called Hund's rule. And what Hund's rule states is that when you're filling, I would say feeling, because I'm from Oklahoma, when you're filling degenerate orbitals, and that means orbitals that have the same energy, like our 2p orbitals over here, you're going to fill them singly first with parallel spins. So what exactly do I mean by that? Okay, so for example, let's say we were going to put electrons into our 2p orbitals. Let's say we had 4 electrons to put in there. Okay, what I'm going to do when I put these in is I'm going to put them in one at a time into each individual p orbital. This is what we mean by saying put them in singly first. So if I have 4 electrons to get rid of, I'm going to put them in, and they're all going to have the same parallel spin, okay? So that's 1, 2, 3. Now that I've filled them singly first with parallel spins, I have one more electron to put in. I'm going to go back, and now I'm going to pair the spin in the first orbital, okay? So when we fill these degenerate orbitals, like the 2p orbitals, fill them singly first, and then go back and pair their spins if you still have more electrons to put in there. Okay, so let's look at lithium, right? This is the big question with respect to lithium. So for lithium, we have 3 electrons, right? And so for lithium, our electron configuration will be 1s2. That's the first orbital that we'll fill. The next one in energy is the 2s orbital. There's 1 electron left to put in there, and so that's it. 1s2, 2s1. This is the electron configuration for lithium, okay? Same thing for carbon. We can do the exact same thing. Carbon has 6 electrons, and so for carbon, we have 6 electrons here. For carbon, the electron configuration would be 1s2. Then it would move on to the 2s, and it would fill the 2s. Then it would move on to the 2p. That's next in energy, and it has 2 electrons to put into those 2p's. And that would be the electron configuration for carbon. Okay, and so we'll do more of these so that it makes a little bit more sense. Okay, so now we're going to get some practice writing these electron configurations. So we just did lithium, right? So we have 1s2, 2s1. If we wanted to draw the orbital diagram for lithium, again, we're going to represent our orbitals as these little boxes. So there are 2 electrons, and we're going to draw them spin up first and then spin down. And then we have 1 electron in the 2s orbital, so we're just going to draw that spin up. So this would be the orbital diagram for lithium. If we move over, we can also draw these as just kind of just solid lines as opposed to boxes. So we would do the exact same thing. So this is 2 different ways you can draw this orbital diagram. But again, I'm going to label these orbitals underneath to let myself know at least which orbitals I'm dealing with. Okay, so then we'll move on to beryllium. So beryllium has 4 electrons. Again, we're at the 2s state, so we filled the 1s first. Now we're going to fill the 2s. So we have 1s2, 2s2, right? And there can be 2 electrons in each orbital because of the Pauli exclusion principle. So again, if I'm going to do the orbital diagrams for these guys, I would have spin up, spin down, spin up, and spin down for both the 1s and the 2s. As we move on to boron, so boron has 5 electrons, so we know we have the 1s, the 2s, both are filled, and so our next orbital that we're going to enter is the 2p's, okay? And so we'll have 2p, and there will only be 1 electron left over to put into the 2p's. If I draw the orbital diagram for boron, I have my 1s, my 2s, so I'll go ahead and spin up, spin down, spin up, spin down, and then I have 2p's. And what I'm going to draw for the 2p's are the 3 2p orbitals. And I'll say this is 2p underneath. Again, there's only 1 electron going in, and by convention, we always just put that in the first orbital, okay? And we always put it in as spin up, because again, using Hund's rule, we're going to want to pair these guys as spin. And we always just, by convention, put it in as spin up. Okay, so for carbon, carbon has 6 electrons, so first 2 in the 1s, second 2 in the 2s. Now, in the 2p, there are 3 separate orbitals, and each orbital can hold 6 electrons. Okay, so for carbon, both of those 2 leftover electrons are going to go in the 2p's. And then when I draw that, I'm going to draw my 1s. Yep, that's real ugly. So I'm going to draw my 1s orbital, my 2s orbital, and then my 3 2p's. So this is spin up, spin down, spin up, spin down, 1s, 2s, 2p. Now again, with Hund's rule, we're going to put them in singly first with parallel spins. Okay, once we fill up those first 3, then we'll come back and pair their spins. Okay, so we can keep doing that, all right, as we move across the periodic table. So we're moving right now from left to right, from boron to carbon, now to nitrogen. Nitrogen has 7 electrons. And again, as we fill, oops, darn it, oh yeah, pen. As we fill these orbital diagrams, we're going to go through 2 in each orbital. And again, when we get to the p's, degenerate orbitals, we're going to fill them singly. Oh, not for nitrogen. Yep, for nitrogen. Okay. So 2, 4, and then 6. 2, 4, 5, 6, 7. Great. Okay, so that's filling the 2 p's with respect to nitrogen. Now as we move on to oxygen, same thing. And then we have 4 electrons to put in oxygen, so we fill them singly first. Now we will come back and pair their spins. Same thing with respect to fluorine. Singly first, pair spins, and then we get to neon. Okay, and so, again, same thing, singly first, and then we pair spins, right? So neon is essentially the filling of that shell, right? That principal quantum number equal to 2, that shell is going to be filled with respect to neon, okay? So if we move up to the next element, which would be sodium, one thing that we can do, instead of having to draw out all of these electron configurations, is we could say, for sodium, I wonder if I do this on the next slide, but anyway, so for sodium has 11 electrons, right? We could draw out the electron configuration as normal, right? We could say 1s2, 2s2, 2p6, and then the next orbital to fill is the 3s, and there will be 1 in that. Or we could abbreviate it and say, well, this thing is the electron configuration for neon, right? We just figured this out, that we filled up neon. It was the filling of that n equal to 2 shell. So we could also write sodium's electron configuration as neon, and then 3s1. Okay, and so what we will tend to do to kind of abbreviate these and not have to write them out and draw them out so much is we will abbreviate any type of filled shell as the electron configuration for the noble gas that precedes it, and then we will write whatever is the leftover part with respect to whatever element we are dealing with. Okay, so I would get some practice at this. So I have you guys write the electron configuration for a couple different things, couple different elements: chlorine, silicon, bromine, aluminum, and then I want you to draw the orbital diagram for sulfur and determine how many unpaired electrons there are. So go ahead and give that a shot. You can write this, the electron configuration, in the full method, right, where you draw out all of the orbitals, or you could also use that noble gas abbreviated version, like I showed you with respect to sodium, where you would abbreviate the filled shell before via the noble gas that essentially the electron configuration corresponds to, and then write out the extra electrons and their orbitals after that. So take some time, try this, and then come back for the answers. Okay, so I'm just writing this out to the side to remind us the order with which we will fill these orbitals with electrons. Okay, so chlorine is first. So we look on the periodic table. Chlorine has an atomic number of 17. That tells us that there are 17 electrons. So if we're going to go ahead and fill this, we'll start with the 1s first. So 1s, 2. Then we move on to the 2s. There'll be 2 in them. So 2s2, then the 2p. There are 3 2p, and each orbital is going to have 2 electrons, so there's going to be 6 total in this. So that is 2, 4, 10. Then we move on to the 3s, and there'll be 2 electrons in the 3s orbital. Then we will move on to the 3p. So 3p for chlorine, there's going to be 5 extra electrons at this point in time, so this would be 3p5. Okay, and again, there's a nice little easy way that we can abbreviate this. This is neon. So this is neon, and then 3s2, 3p5. Okay, so same thing for silicon. So I tend to get into this habit where I just start filling these orbitals because I'm fairly familiar with them. But again, if you're not understanding, make sure to come and see me during my office hours this week so that I can hopefully help you understand how this orbital filling occurs. Okay, so then silicon has 14 electrons. So again, we're going to start with the 1s, fills first, 2s, 2p6, then we move on to the 3s, so that's 2, 4, 10, 12, and then the next orbitals are the 3p, and so there's only 2 of them in there for silicon, and again, we can abbreviate this as neon, and then 3s2, 3p2. Okay, bromine's a little bit bigger. It's got 35 electrons. So again, same thing, 1s2, 2s2, 2p6, 3s2, 3p6. That is the filling of the third shell, the third principal quantum number. Then we move on to the fourth. So we've got 4s2. Now this is where we had just filled this guy over here, 4s. Now we're going to move into the 3Ds, okay? And so remember that Ds have 5 orbitals each, okay? And so that means if 2 electrons go into each orbital, then 10 electrons will go into that 5D orbital, okay? So 4s2, then we move to 3D10, and then for bromine, after 3D10, we'll move into 4p, and then there's 5 electrons that go there, okay? So again, this filling of the third shell is represented by the noble gas argon, okay? So this could also be written as argon, 4s2, 3d10, 4p5. Okay, and so last one, aluminum. Aluminum's a little bit easier. It doesn't have that many electrons. Well, 13. So 13 electrons. So same thing, 1s2, 2s2, 2p6, 3s2, and then 3, not D, 3p, and then for aluminum there's only 1 that goes into that. And again, this can be abbreviated by neon, 3s2, 3p1. Ugh, orbital diagram for sulfur. That sounds terrible. Okay, so sulfur. Sulfur's down there. It's below oxygen. It's got 16 electrons. Okay, so if I draw the orbital diagram, I'm not going to draw boxes because that's just going to get to be too much. So we've got 1s, we've got 2s, we've got the 2p's, we've got 3s, we've got the 3p's, and yeah, that's where sulfur is at. So we've got 2, 4, 10, 12, 13, 14, 15, and 16. Okay, so this would be the orbital diagram for sulfur. That's nice. And so then the last little bit of this is, hey, how many unpaired electrons do we have? So any of these orbitals where we have these electrons that are matched up, these are called paired electrons, right? So there are only 2 orbitals here that are unpaired, okay? These 2 electrons are unpaired. So there are 2 unpaired electrons in sulfur. Again, because everyone else has been spin paired. Okay, so time for another question. All right, so what are the 4 quantum numbers for each of the 2 electrons in a 4s orbital? So as a reminder, the orbital is specified by our 3 quantum numbers that we originally learned in L and M sub L. And then the electrons themselves are specified by the 4th quantum number, M sub S, and it can only take on 2 possible values, right? So 1 plus 1/2 and minus 1/2, okay? So think about this, and then pause it, come back for the answer. Okay, so we have 2 electrons. We're trying to specify the 4 quantum numbers for each of them. So I'm going to call this electron number 1 and electron number 2. And these guys are in the 4s orbital. And then above them, I'm going to write N, L, M sub L, and then M sub S. So I'm going to specify the actual numbers. All right, so the 4s orbital, all right, so the principal quantum number is always given first. The L is given second, right? So our principal quantum number here is 4. For S orbitals have a L equal to 0. And then for M sub L, there's only one possible value for M sub L. That's also 0. So for both of these, we'll have 4, 0, 0, and then 4, 0, 0. And then their only other point of difference will be M sub S. So we'll give the first electron the spin up, the plus 1/2, and the second electron will be spin down, minus 1/2. Okay, so again, the orbital is specified by N, L, and M sub L, and then the electron itself is specified by M sub S. Okay, so we're going to define 2 different types of electrons in an element, right? So let's take silicon, for example. The electron configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2, okay? So notice that these first electrons are filling, essentially, the first and second shell, right? This is essentially the electron configuration for neon, right? And this is, again, filling both the n equal to 1 and n equal to 2 shells. So these are electrons that are in filled shells. We then have these electrons, right? These electrons are in their outermost principal energy level, and they tend to not be filled, right? So this outermost principal energy level is n equal to 3. And that shell, with respect to these electrons, that shell is not filled, okay? So these electrons that are in this innermost lower filled energy shells, these are what we call core electrons. And these guys that are in this outermost principal energy level, these are called valence electrons, okay? So valence electrons, again, are the electrons in the outermost principal energy level. Core electrons is everything in inner shells that are filled. I can't really state that well, right? But you get what I'm trying to say. Okay. So anyways, what's the big idea behind valence electrons? So if we go back to the periodic table, and we look at how we've essentially differentiated various parts of the periodic table before, when we talk about elements that lie in the same column, we talk about elements that are in the same group, right? So columns we call groups. And the big thing about elements that are in the same group is that they have very similar chemical properties, right? So if we now consider that with respect to things that we have just defined, with respect to valence electrons, we will note that everyone in the same column has the exact same valence electrons, right? So everyone in group 1A, these guys were the alkali metals, they all have their valence electrons as 1 electron in an outer s orbital. Okay, same thing for the alkaline earth metals. They all have 2 electrons in that outer s orbital. Okay, so again, valence electrons that are in the outermost principal energy level, these guys tend to be held the loosest, right? And so they're going to be really important with respect to reactivity and bonding, and that's exactly what we see with respect to our groups in the periodic table. Okay, so a couple more things. So we did 1 electron configuration no, we haven't done a metal yet. Okay, so we have done 1 electron configuration where we had to include the d orbitals. I think we did the electron configuration for bromine. So bromine was, I'm just going to go ahead and abbreviate it. It was argon, and then it was 4s2, 3d10, and then 4p5, okay? But we haven't actually talked about the electron configuration for any of the transition metals, which happen to be these d orbitals, okay? So now remember that when we were looking at the energy levels, we had found that the 4s orbital was actually at a lower energy state than the 5 3d orbitals, even though 3 is a lower principal quantum number, okay? So what we'll find here with respect to electron configurations for the transition metals in this D series is the fact that this difference in energy between the 4s and the 3d is actually very small. So sometimes we will get kind of irregular electron configurations because of that, okay? So in general, usually these guys will have their 4s filled, right? And they'll start to fill their d orbitals. So we can see that with scandium. As we keep going across, we're filling the d orbitals. But then when we get to chromium, you would expect the electron configuration here, if we were following the exact same pattern, to be 4s2, 3d4. But instead, what we find is that this is 4s1, 3d5, right? The idea behind the 3d5 is that with 5 electrons, when we put them into the d orbitals, that essentially fills the entire D shell halfway, and there is just a peculiar mechanical stability to half-filled shells, right? And so what has happened here is chromium has essentially taken one of those electrons from the 4s and has promoted it to the 3d, okay? And again, what that ends up with is a half-filled S shell and a half-filled D shell. But again, that's just energetically more favorable. And I can't necessarily explain the reason why, just to tell you, hey, half-filled shells tend to be better or more energetically favorable. So how do we know that this is the case? So for the majority of these guys, they have to be experimentally determined, right? So what they found experimentally is that chromium actually has 4s1, 3d5, okay? So then as we move on, magnesium, we go back to our normal filling. So this is 4s2, 3d5, 4s2, 3d6, 4s2, 7, 4s2, 8, and then when we get to copper, we get another irregular filling, right? You would normally think, or if we were going just in the way we've learned it, that this would be 4s2, 3d9, but instead what happens at copper is that it is 4s1, 3d10. The 3d10 is a complete filling of the d orbitals, right? And so because, again, that is just energetically better for copper, it will take one of those 4s electrons and put it into 3d to fill the 3d entirely, leaving the 4s, halfway filled, okay? And then we get to zinc. Zinc's fairly inert. It's got a filled S as well as D, okay? So on that first row of the transition metals, we get an irregular copper and an irregular chromium. So copper and chromium are irregular. As we move farther down, we get a lot more irregularity in the second row. So for example, 42, what is that, rubidium? I don't even know. So this guy's weird. Molybdenum is weird. Ruthenium is weird. A lot of them are weird, right? So there's lots of different ones that are weird. What I would be kind of concerned with here is maybe knowing the irregular configurations in this first row of the transition series. I wouldn't be concerned necessarily with the second row, though. Okay, I think that is it for the transition metals. Again, it's because this energy spacing is so small between the 4s and the 3d that we actually see these irregular configurations due to irregular filling. Okay, so another question. On the first part, I want you to write the electron configuration for germanium and identify both the valence and core electrons. And then the second question, I want you to write the same thing for tin and identify the valence and core electrons. So take a moment on that one, write it out, and then come back for the answer. Okay, so germanium. I don't know why I do this germanium and tin because they're like right on top of each other. Germanium, we'll go ahead and write the full electron configuration for. So we're going to go down here. My iPad is not happy with me. So GE, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we get to our 4p's. 4p, and then for germanium there are 2. Okay, so this is the electron configuration for germanium. Again, you can abbreviate this as argon, which is this guy, 4s2, 3d10, 4p2. Okay, now let's identify the valence and core electrons, right? So I told you previously, and I probably didn't tell you all that well, that the valence electrons are the electrons that are in the outermost principal energy level, okay? What that means is the thing with the greatest N, right? Greatest principal quantum number, okay? All right, so when we look at germanium, we find that we've got a bunch of filled things, but the greatest N, the greatest principal quantum number, are the 4s, okay? These are the valence electrons, okay? So the valence electrons, let me maybe use a different marker. The valence electrons for germanium are the 4s2 and the 4p2, not the 3d, because the 3d is part of the filled lower energy levels, okay? So for valence, maybe I shouldn't have used the blue for those guys. For valence, we've got this and this. These guys are our valence electrons. For the core electrons, we'll move back to red. We've got all of these guys as well as the 3d10, right? These guys in red are the core electrons, okay? All the electrons that are in the filled lower energy levels. Okay, so same thing for 10. I'm going to go ahead and abbreviate 10 because I'm lazy. So 10 is krypton. Krypton, and then 5s2, 4d10, 5p2. So same idea here. What are our valence electrons? It's these electrons in the outermost principal energy levels. So we've got these guys as our valence. And then for the core, we've got all of these electrons that are in this filled krypton shell as well as this filled 4d shell. Because again, it has a 4 in front of it. And this is part of one of our lower principal energy levels. Okay? Okay, valence and core. Okay, so this is a nice little summarization of what has happened thus far. Okay? We kind of introduced this idea behind quantum mechanics with the idea that, hey, we don't know what is happening with electrons and atoms, right? We want to figure that out. Also, one of the big promises that I mentioned at the very beginning of this chapter is the fact that, well, quantum mechanics is going to help us explain why the periodic table is actually the way it is, right? So we had periodic law and Dmitri Mendeleev, and he had just noticed some things, and he had arranged the periodic table in that way. But we didn't have any type of theory or any type of model to help explain that. Now, with quantum mechanics, hopefully you can see why the periodic table is the exact way it is, right? So if we look at it, we will find that in these first two columns, this is filling the s orbitals, right? There are 10 columns across the transition series because this is filling the d orbitals, right? So there are 10 d orbitals. That's not how you spell orbital, but just stick with me. 5 d orbitals, pardon me. 2 electrons go into each one, so this can hold the total of 10 electrons, 10 columns across. These guys over here are 6 columns wide because, again, who are we filling? We're filling the p orbitals, okay? And then the lanthanides and actinides are 14 columns across because we're filling the f orbitals, right? This is why the periodic table is the exact way it is, because we're filling these various s and p and d orbitals, and that's why we get the number of columns that we do, okay? Okay, so notice also, one more time, with respect to the column, what we're going to need to know later on is that the column number is going to tell us the number of valence electrons that are in whatever atom we're interested in, right? So we've already talked about valence electrons. That directly correlates to which column you're in, okay? Number 2, when we talk about rows, so when we talk about rows in the periodic table, What the rows correlate to is the principal quantum numbers, right? The first row is filling n equal to 1, right? The second row is filling n equal to 2, so on and so forth, okay? Okay, so that is it for this chapter. I will move on to chapter 7 in a separate video.